Ever feel like scientific progress is kind of like watching paint dry?
I can see that.
We're told bigger, better experiments are the key. But this research paper argues it's not that simple.
Yeah.
At least not for the Large Hadron Collider.
Right.
It's like upgrading to a fancy sports car but not knowing about the turbocharger under the hood.
Oh, I like that.
The real potential is hidden.
It's a fascinating challenge to this idea that discoveries at the LHC are limited by a square root relationship with data.
Okay, break that down for me.
Imagine this. You want a discovery twice as precise. You might think you need 4 times the data.
Makes sense.
This paper says, not so fast.
So it's not just about the raw amount of data, but how we analyze it. That's kind of exciting, like realizing there's a whole new level to the game we didn't even know about.
Exactly. The paper uses the top quark as a prime example.
Top quark rings a bell.
It's the heaviest known fundamental particle.
Okay.
Imagine a tiny speck as heavy as a gold atom.
Wow.
And understanding its properties is huge GE for particle physics.
Right. I remember reading about the top quark. It's like the VIP of the particle world. But why is it so important?
Well, the top quark's mass is directly connected to the fundamental forces of the universe, the forces that dictate how everything interacts.
Uh-huh.
Getting a precise measurement of its mass is like finding a missing puzzle piece to how the universe works at its core.
Okay, so a tiny particle with big implications. But how do we even measure something that small, let alone accurately?
That's where the ingenuity comes in. Scientists have been using this cool technique where they look for top quarks that are boosted,
Boosted.
moving crazy fast.
Gotcha.
Think of it like this. It's easier to study a fast-moving hummingbird when it's in a straight, predictable flight path than when it's flitting around randomly.
So they're basically putting these top quarks on a racetrack to study them better.
Essentially. And by focusing on these boosted top quarks, they've already achieved a level of precision in their mass measurements that goes way beyond what the old square root thinking would predict.
Nice.
And there's another exciting example. The search for the incredibly rare event of 4 top quarks being produced simultaneously.
Hold on, 4 of them at once. I can barely handle hearing about one. How rare are we talking?
Okay.
4 top quarks at once. That sounds ludicrously rare.
Ugh.
Like finding a 4-leaf clover in a field of regular clovers, but then finding 3 more just like right next to each other?
A fantastic analogy. It's exactly the kind of rare event that might make you think we'll never have enough data to study this properly. But here's the thing.
What's that?
This paper highlights how, by using advanced analysis techniques like boosted decision trees, they're finding these 4 top quark events at a rate that defies those old square root limitations.
So it's like those boosted decision trees are acting like superpowered 4-leaf clover detectors.
Exactly.
Yep.
They're helping us sift through the massive amounts of data generated by the LHC to pinpoint those incredibly rare and valuable events.
Okay.
And it's not just about the top quark either.
Really?
The paper goes on to highlight other areas where this new way of thinking is revolutionizing particle physics.
All right, I'm ready for more. What other hidden treasures are we uncovering?
Well, let's talk about the Higgs boson for a moment.
The Higgs boson.
This is the particle that gives other particles mass, the one responsible for making the universe as we know it possible.
Right. The Higgs boson, the celebrity of the particle world. I've always been a bit fuzzy on the details, though. What's so special about it?
The Higgs boson is fascinating because it represents a completely different type of particle than anything we'd ever seen before.
Interesting.
It's not a building block of matter like quarks or electrons,
Oh, okay.
and it's not a force carrier like photons or gluons.
Right.
Instead, it's a fundamental component of the mechanism that gives other particles mass. It's like the conductor of an orchestra. Without it, the other particles would be a jumbled mess.
Okay, that's a pretty important job. So how does this paper suggest we study the Higgs boson in a way that goes beyond the square root limitations?
Well, one of the key insights is that to truly understand the Higgs, we need to look at it from all angles. This means studying not just how often it's produced, but also how it decays. What particles it decays into the directions those particles travel, how much energy they have. It's like trying to understand a city by not just counting the buildings, but also looking at the architecture, the traffic patterns, the way people interact within it.
So it's about painting a complete picture of the Higgs, not just a rough sketch.
Precisely. And this is where the paper gets even more interesting. It argues that there are certain aspects of the Higgs that are currently hidden from our view, like trying to solve a jigsaw puzzle with missing pieces.
Missing puzzle pieces, what do you mean?
They're called blind directions. and they represent limitations in our current
Yeah.
experimental and analytical methods. They're like blind spots in our vision, preventing us from seeing the complete picture of the Higgs boson.
Blind spots in our vision.
Yeah,
That sounds frustrating. How do we get rid of them? Blind spots in our vision. That sounds frustrating. How do we get rid of them?
that's the million-dollar question. And this paper argues that the answer lies in a two-pronged approach. First, we need to develop more sophisticated analysis techniques.
Right.
Tools that can tease out subtle patterns and correlations in the data that might be invisible to our current methods. Think of it like upgrading from a magnifying glass to a high-powered microscope.
Okay, so better tools for a better view. But you mentioned a two-pronged approach. What's the second part?
The second part is equally important.
Okay.
It's about shifting our focus from simply collecting more data to deeply understanding the nuances of the data we already have.
Interesting.
This means paying close attention to the kinematic details of each event.
Kinematic details.
Things like the precise energies and trajectories of the particles involved. It's like the difference between looking at a map and actually walking the terrain yourself. You notice details and make connections you wouldn't otherwise see.
So it's not just about the what of the Higgs boson, but the how, the where, the when, all those little details that tell a bigger story.
Exactly. And by combining these advanced analysis techniques with a more nuanced understanding of the data, this paper suggests we can start to illuminate those blind directions and finally see the Higgs boson in its full glory.
This is blowing my mind. It's like we're not just passively observing the universe anymore, but actively interrogating it, trying to unlock its secrets.
And the most exciting part is that this new approach has implications far beyond the Higgs boson. By embracing this combination of cutting-edge technology and deep theoretical understanding, we're entering a new era of particle physics, one where the potential for discovery is limited only by our own ingenuity and imagination.
So it's not just about bigger and better particle accelerators, but about bigger and better ideas.
Precisely. It's about approaching the unknown with a sense of wonder and a willingness to challenge our assumptions. And that's what makes this paper so inspiring. It's a call to action for the entire scientific community to embrace a new way of thinking, a way of thinking that could unlock some of the universe's most closely guarded secrets.
This deep dive has been a wild ride. We've gone from the limits of the square root to boosted top quarks, rare events, and the elusive Higgs boson. It seems like the future of particle physics is anything but predictable.
And that's what makes it so exciting. As we continue to explore the subatomic realm, we're bound to encounter even more mysteries and challenges.
Yeah.
But armed with our curiosity and our ever-evolving toolkit, I'm confident that we'll continue to push the boundaries of human knowledge and unlock a deeper understanding of the universe and our place within it.
Beautifully said. And to our listeners, if you're ever feeling limited by the so-called rules of any field, remember that sometimes the most groundbreaking discoveries come from questioning those rules and daring to imagine a different way forward. Keep those minds curious and those questions coming. Until next time.